I don't see anybody coming anymore, so why don't we start a minute early? That gives you more time, right? Good morning, everybody. It's my pleasure to announce Tobias Glasmacher for this keynote this morning. Tobias has been with the Ruhr-Universität Bochum since 2012, if I see this correctly, and you're a full professor since quite a number of years already there, and with your background in mathematics, which is amazing. Of course, we are looking forward to your presentation on additive drift, which is all we need. Thank you.
Yeah, thanks for the introduction, and also thanks a lot for the invitation. It's very nice to be here and present some work on evolution strategies, some of what is mine and some, of course, by others. Let's see. Okay, this is working. So motivation for what I want to do today is, if you want to analyze an algorithm, there's always a trade-off between the strength of the result you can get and the effort you have to put into the analysis. And of course, the simplest thing is like, oh, you wave your hands and do some very rough estimate, and that's probably very quick. And the highest possible goal would be like to have a really exact description of, say, runtime of an algorithm for achieving some goal, which is typically, out of reach in terms of like the effort you would need to put in. And then there were several things in between, in particular for evolution strategies. This progress rate analysis has brought us pretty far, in particular in terms of like a good intuitive understanding of algorithms, but it doesn't give you exactly, say, strong results, not in the sense of like that we don't understand anything, but strength here is really to be interpreted in a more strict mathematical sense, so getting guarantees out. And the two techniques that are around for analyzing evolution strategies with some success are Markov chains and drift analysis. So we do have some quite good results with Markov chains now, but I want to argue in this talk that we should also do more drift analysis and push that a bit more, because I actually think if I see what effort already went into making this whole Markov chain analysis work, you can see that it's pretty high up here in this effort category. And I think that in some sense, we can actually maybe get more powerful results. In a sense, you will see exactly in which sense by using drift with potentially even a bit less effort. But that's, of course, my bit subjective view or hope on this thing. So what I'll cover is I'll talk about evolution strategies, what they do, and what I'm interested in terms of analysis. Then go through these different analysis methods, Markov chain analysis, drift analysis, with a particular focus on covariance metrics, adaptation, having that, not having that, what difference it makes and what challenges it poses. And then I'll talk quite a bit about how can we actually construct a potential function. Potential function is then the thing we use in drift analysis to describe the state of an algorithm and the progress it makes, from which we finally can derive runtime guarantees. So what's an evolution strategy? So who here in the audience is working with, say, in any sense, continuous domain algorithms? That's quite a few. That's not so bad. So assume that many of you know what an evolution strategy is, but I know that, okay, many people are also just purely in the discrete world. So let me tell you what this is. I look to start with the variables that make up the state of this algorithm. So at each point in time, we have some location, some vector m, we have a scale parameter or step size parameter that tells us how far from that location we try to find new locations. We have this shape parameter c, which is the covariance matrix. We'll come to in what exact sense this is a shape parameter in a second, looking at figures. And then if you look at fully fledged CMA-ES, there are two different so-called path vectors that also contribute state variables, but I just ignore them in the rest of this talk because they are somewhat non-essential for really understanding the core mechanisms. And then the algorithm, basically that's the standard evolutionary algorithm scheme. We sample some offspring, lambda of them. Very often lambda will be 1 here, so very simple. And we sample that from a normal distribution centered on this vector m, and with a covariance matrix that consists of basically two components. We have the shape parameter C, which we also call covariance on the slight misuse of notation. And we have this scale sigma square in there. And then, of course, we rank our individuals by fitness, or we compare to the parent or something like that. And from that, okay, you can then update the evolution path. But then the really important part is, of course, we want to update the state that like makes up this search distribution. We'll update the mean, the step size, and if we have one, also the covariance matrix. So that's quite abstract. So let's look at what this means in terms of pictures. So here is some not so badly conditioned ellipsoid function. So this little flag here is the optimum, and you can see the level sets. And then we start with some search distribution, which is just an isotropic Gaussian. So the mean vector is here in the center of these green circles. But this is this bell-shaped curve, really, kind of in all dimensions. And this bold green circle, say, is one standard deviation. Now we sample offspring. Okay, that's a lot of offspring for a 2D case, but it's really just for illustration purposes. You can see like this guy over here is kind of in the innermost level set. So this is the best point. We will typically not use only the best, but a couple of best points. And then update all the parameters. Maybe get a next search distribution. You can see that the mean moved from the center of this green circle to the center of this blue ellipsoid. The shape parameter, the step size increased, which is simply the blue ellipse is bigger than the green circle, and the shape changed. So we elongated the variance in this direction simply because we moved there, and there's this assumption that if something was beneficial now, it's probably going to be beneficial in the near future. And if we keep doing that, now we reduce the figure a bit, show you many iterations at once. At some point, we'll hopefully move towards the optimum. And importantly, the shape of our distribution will adapt to the shape of the level sets. And that's what covariance matrix adaptation does. If we don't have it, we are stuck with circles all the time, which are not well adapted to the problem. So, and if we then keep going, what happens is these ellipse shapes, they stay more or less the same. Of course, there's random fluctuations. It's a randomized algorithm, right? But we zoom in, and that's really the convergence phase. That's when we really make a lot of optimization progress. And now what I can do, I can apply an affine transformation to this. Because the algorithm with covariance matrix is fully affine invariant, provided that we also transform the initial conditions, right? So I can make my ellipsoid function a sphere function, make the level set spherical by just means like transformation of the coordinate frame. And that gives me, of course, like now an extended initial distribution, but there's no principal problem with that. And I can understand everything in this picture. Another transformation I can do is I can now start zooming in here. And then I see, okay, this is really just zooming in that one figure. If you look at some ellipses that are like nearly circular, and then you zoom in and they keep being nearly circular, so up to random fluctuations, we always have the same picture. And that's two important invariance properties. This is like called behavior, okay, and invariance. So we have this affine invariance, in particular scale invariance. So at each point in time, once everything is well adapted, the situation kind of looks the same, and we make a certain progress, hopefully, towards the optimum. So this is figures spit out by Nico's CMA package. So just pay attention here to this big blue line. That's basically optimization progress over time. And this is really, say, this is distance to the optimum or squared, doesn't really matter, on a log scale. So you can see initially, well, we make some progress, but then in this last part, the curve is much steeper. We make much more progress per time. That's where we want to get. And this picture, this is basically the eigenspectrum of this shape matrix, of the covariance matrix. You can see we start with all one eigenvalues. That's this isotropic circular distribution. And then the eigenvalues start to split up. There's a 20-dimensional ellipsoid function now. And until they are well adapted, and then they stay more or less the same. Okay, they drift all together, but the distance between them stays the same, and that's what determines the shape. And then you can see at this point, where they are well adapted, we start to be much, much faster. So a lot of time goes into covariance matrix adaptation, and then the actual optimization phase is short. Yeah, so that's a typical behavior we see in practice. And so I look a lot at the sphere function in this talk, and I want to just quickly convince you that this is a meaningful thing to do, in particular if you have covariance matrix adaptation. It's much more meaningful than, say, looking at one max function in discrete domain, but we can fight about that, of course. And that's simply because if we are a bit lucky and our function is somewhat regular, it's somewhat smooth, twice continuously differentiable, you can apply Taylor's theorem. And for the purpose of convergence, we can argue that all local optima are essentially convex quadratic functions, unless there's a zero eigenvalue. Yeah, and therefore, like then after applying this invariance argument, the sphere function is essentially all we need, right? That's for this asymptotic effect, like very late phase of convergence, like convergence speed, the slope you saw in the end. Yeah, of course, that's not the complete picture. Of course, there's multimodality. You may have like some asymmetric attractor, which is then not C2. You may have plateaus like discontinuities, noise, and many things. Okay, we are not there yet. First things first, let's start with the simplest case as usual in theory. Maybe in 10 years from now, I can give a different talk. Okay, so what do I want a runtime analysis for such an algorithm to do? What questions should it answer? And one classic question is, of course, how does the runtime scale with whatever number of variables? Like what if I add a variable? What I double the number of variables in my problem or problem dimension here, right? Then does the runtime double, scale, quadratically, exponential, whatever? Okay, it's linear. We know from experiments we want that described. Problem in instance. So I said I talk mostly about the sphere function, and that is enough for like that final slope. But how long does it take to get there? How long does it take to adapt the covariance matrix? Yeah, so really I want these two different things. Describe the convergence rate, the final slope, and how long does this transient phase until I'm in that kind of stable regime where I just converge? How long does that take? It's an important question simply because it takes a lot of time, often the lion's share of the optimization time. So convergence rate is not the full picture here. Yeah, so that's my wish list. And I'll not really get there, but we'll see different techniques covering different parts. So let's start with Markov chain analysis. So that goes back roughly 20 years. And basically, yeah, all or most of the work was done in Anauger's group. Started out with the analysis of a relatively simple 1, lambda algorithm, but the main thing is to develop the tools at this point. And what you get is then this scale invariant behavior. So you have a distribution of, say, typical states once everything is nicely adapted. And then basically always the same thing happens. I showed you this zoom in. Yeah, either you zoom in or you zoom out. If you zoom out, that's bad, like you diverge, like, well, this analysis cannot exclude that, but of course we know from experiments that it doesn't happen. So basically this gives you not only this converges at a linear rate. Yeah, so the convergence is somewhat fast, and we know that these types of algorithms cannot converge faster, so best case. That's already a lot, but then it took a lot of time to develop good tools. And that's what, like, remember this very first figure where I showed this green curve with the effort and the strength of results. And here comes a lot of effort, like basically each of these bullet points is at least one PhD thesis or so, yeah? So what they had to do is really extend standard results on Markov chain theory to cover certain discontinuities that come from rank-based selection. So and Alexandre did a really awesome job in doing all of that. So that's only technicalities, that's only preparation. Yeah, and then finally, last year, Armand was in the position to use all these results, put it all together, put a lot on top, like by himself, to actually prove linear convergence of CMA-ES, which is the first time we have like any serious mathematical statement about the fully fledged CMA-ES and many variants he covered. So this is really a seminal result in my point of view. So how does that go, that analysis? How does that work? Like, okay, no details here, but from a bird's eye perspective somewhat. So the first observation, like even with a very simple evolution strategy on the sphere function, okay, so we continue like this. So the process is scale invariant. That's this, in that late phase, you can just zoom in, and situation is always the same. So if step size adaptation does its job, then the step size will be proportional to the distance to the optimum, which for the sphere function is just the norm of that mean vector. Okay, and if that is the case, yeah, which we don't know yet. I mean, we know from experiments, of course. Then we can split the behavior into two parts. The first is just this norm of M. That's optimization progress. That's what we really want. And the rest is just auxiliary. Yeah, so this fast convergence will only happen if the step size and the covariance matrix potentially is well adapted. Yeah, and to describe this, how well is it adapted thing, we have this other variable, theta. This is all the simple case without covariance matrix. Yeah, so we can just look basically at where are we compared to like step size. You somehow have to set this norm of M and the sigma in relation. If you do this with covariance matrix adaptation, it's a bit more complicated, but you can still recognize like this M divided by sigma is over here. There's this nasty normalization term. And this term isn't actually that scary. So the C is the covariance matrix. The H is the Hessian of the problem. And this is basically, if everything is well adapted, this is the identity matrix. So this measures basically the mismatch in shape. Yeah, and then you have to normalize with a smallest eigenvalue or some quantity to make it well defined and basically take the step size component out. Well, okay. So this is maybe not the formula you want to work with and do bounds with and so on, but that's what Armand did. Okay, but the important thing is really just this distinction between the two components. Yeah, so initially, like this is the same figure as before. So what happens here while we change the shape of the covariance matrix, basically this one turns towards something close to the identity matrix. Yeah, and then in this phase where we really optimize quickly, actually nothing changes anymore in this part. Yeah, so once we are kind of stable in that optimal or around that optimal state, we make a lot of progress here, but not much change over here. So that's a behavior we would like to show or formalize. Yeah, and then if I do all these transformations here, everything is basically invariant with respect to that. Yeah, okay, you may have to change the norm you're using here, but like this thing is by design invariant to these things. So that's why it's designed this way, and I think it's easier to understand it geometrically than with the formulas. So, okay, once we have this problem decomposition, so the one component, that's the higher dimensional component, we want this to be stable around an optimal configuration of parameters, and if it's somewhere far away from that, we want the adaptation to drive it there. And once it's there, then we make a lot of progress here. If it's not well adapted, this is actually not moving. And the common selection strategy can even get worse. So, and in Markov chain analysis, this stability, it basically means the theta, which is, of course, a Markov chain, then follows a stable limit distribution. It exists. We don't know what it is. Could be crazy. Yeah, hopefully it's somewhat concentrated around the good states. But all we really need in the analysis is it exists. That's not very strong in a sense, and that gives limitations on the type of results you can get. So, and in order to get that, like, that took 20 years. So that's hard enough, yeah? So you need to go through many steps, like you need to prove many properties of your Markov chain, like it's irreducible, it's aperiodic, there's recurrence, and then you finally, at some point, get to geometric ergodicity, and that's basically what you want. Yeah, each of them one PhD thesis, let's say, well, very roughly in terms of effort. So this is like a drastic reduction of complexity on the slide. So now the logic is a bit like this. Imagine for a moment that we have this theta completely fixed. That would mean basically your search distribution relative to the optimum always looks the same. And then you do a step, and then you may have, you know, kind of zoomed in or out a bit, but it again looks the same. That's not going to happen. That's really just a consideration. What if that would be the case? Yeah, then all that could happen, okay, we have some distribution of successor states. We could, on average, come closer to the optimum by a factor or move away. Like, hopefully, the likelihood of moving in is much better, like bigger than like of moving out, or at least the probability of states in which we systematically move inwards in that stable limit distribution dominates, yeah, because then we actually converge at a linear rate. And well, now, if we don't keep the theta fixed, the same consideration still applies. All we need to do is take the expectation over the stable limit distribution, and then, of course, hope that, again, this convergence part dominates. And that is what Amon was actually showing, and there's a lot of like technical effort in getting that done. And what you have achieved if you did that is, well, we get linear convergence of CMA-ES, which we didn't have for 20 years. Yeah, it was a long-standing open problem. And the important thing, we get this at a convergence rate, so this slope in that plot, that is independent of the problem instance. Yeah, so everything is as fast as in the simplest case, namely on the sphere function, eventually after adaptation. So that's awesome because it means, like for the first time, we have a mathematical statement that says CMA-ES not only like does not harm or like statements like that we had before and they were kind of weak, but now we have a statement that says it helps. It does exactly what it's designed for. So that was really an important one in my point of view. So this is, for example, something you don't have in a gradient descent, but you have in Newton steps. Yeah? But, well, the analysis is somewhat unsatisfactory in other ways. Yeah, so we have no control over what that stable limit distribution is. Absolutely none. Could be anything, could be kind of inefficient. So we don't know, like, what that convergence rate is. So if we look at two consecutive states, maybe the log distance to the optimum, you would expect that to decay by an additive term, by an additive constant, if you have linear convergence. Well, we don't get this expected value because we have no idea what the distribution is. So no value for the rate. We know there exists a rate, it's independent of the problem instance. Amon also showed that this difference is negative, so goes in the right direction, but no value. Can't tell you how long it will take in terms of runtime analysis. So no convergence rate, and also we don't get dependency on the dimension with this approach because we don't know how the distribution changes if we add new variables. Also, no idea how long will it take to arrive at or close to that stable limit distribution. So how long will the covariance matrix adaptation phase take? All of that cannot be done. Still, I think an extremely important progress. And actually the only thing we really have for fully fledged CMA is. Okay, so the other story, okay. So the question, just for the recording, right? I mean, the question is, does the analysis start when everything is well adapted, or do we also show that you actually get there, the second one? So basically you can start anywhere in state space. which is important, right? For this sphere function I showed you, well, you can basically replace any convex quadratic with a sphere if you transform the initial conditions accordingly. So we really, in order to make this meaningful, it has to work for all initial conditions. Yeah, and then basically this Markov chain converges towards its stable limit distribution. Yeah, but how long it takes and so on, no idea. Okay, so the big competitor method, we don't perceive it as competition, but I mean, the other thing we could do really is drift analysis. And that basically goes back also 20 years. And it wasn't really termed drift analysis at the time. There was all this work by Jens Jägersküper who analyzed the 1+1 evolution strategy without covariance metrics. All this, of course, started with simple algorithms. And he had analysis basically showing the correct dependency on the runtime on the problem dimension and also on the problem instance in the sense of looking at the conditioning number of the Hessian. So how elongated is that ellipse he took into account. So actually, if you look at his proofs, you really have to read in between the lines, and then you will find some drift arguments. It's not explicit. It wasn't really well developed at the time in this community. So what we then did in 2018 is to actually took that well-developed framework of drift analysis and show a similar result. Actually, this first one was even only for the sphere function, but it was extended in particular by Daiki and Yuhei in the coming years. So these are both very nice papers. The one actually here, I think it got Best Paper Award at FOGA, generalizing it to a huge class of functions. So not convex quadratics anymore, but all strongly convex functions with Lipschitz continuous gradients. So this is not a parametric class. This is a non-parametric, really huge class of functions that's also often analyzed in ingredient-based or DFO algorithms and so on. So this really puts us in a much better position, but all without covariance matrix adaptation. And here basically complementing, the last one complementing Jägersküper's result on basically dependency on the problem instance. So they do a very fine-grained analysis, not only taking the conditioning number, but basically the full spectrum of the Hessian into account and showing the dependency on of the runtime on this. So all of that without covariance matrix adaptation, we currently don't have any drift analysis that takes that into account. So how does that argumentation, like how does that analysis work? I guess many people here are familiar with drift. I hope everyone has at least heard the term. So here, this is the only theorem in my presentation. And as you can see, it's not even mine. Yeah, I'm just using this stuff. And yeah, had a discussion with Martin yesterday. So we may have to work on some technicalities, like prerequisites may not even be exactly precise and so on, but it doesn't really matter. Like this is all probably fixable, and it doesn't matter for that high level overview of the arguments which I want to present here. So think like you have some sequence, X, T is iteration index of your algorithm, and what exactly that X describes, I'll get to on the next slide. For now, it's just important that we're starting somewhere on the real line. So this is a process on the reals, and we're starting at a big value, and we want to get to a smaller value. And we're asking how long does that take? So T is what we call our stopping time. So this is the first time we go to the goal or to the left of the goal. And what we have available to drive the process there, it's a stochastic process, is this delta. So we have a positive delta so that like the single step progress is at least delta in expectation, but there's no real control over the distribution. So there is some distribution of steps. Think of these green arcs as actual, say, samples from that distribution. So for simplicity, I put this red Gaussian up there. This is, of course, never a Gaussian. This is some crazy distribution that depends on your algorithm. And the idea is, okay, all we need to know is that on average, right, this black arrow at the top is essentially the delta. On average, we move to the left by something. And then this is drift with overshooting. What we are asking now is, okay, if we do then this sequence of steps, so say we are lucky and we're actually moving to the left all the time, which doesn't have to be the case in general. Yeah, I mean, there are these green arcs to the right. Yeah, that at some point we don't arrive at the goal, we arrive somewhere else, and then you can basically bound the expected runtime. So that's a very powerful translation, yeah, between single step progress, some distribution, no good control over that, to a completely different beast, which is a runtime, which then also has some distribution, no idea what it is, but the expectations translate in a very intuitive way, namely as if this was a deterministic process. If you would move to the left by exactly delta, right, then you would expect the distance covered divided by delta as the number of iterations you need. And that holds an expectation. So that's pretty cool, and that's the power of drift analysis or drift theorems. So in my job now as a user of this theorem is to design this X in such a way that it's meaningful for a runtime analysis of an evolution strategy. Okay. And in order to do that, we start with the exact same problem decomposition you've already seen for Markov chains. So we separate this optimization progress component and this parameter adaptation component. And actually, what will be this X is a function of the algorithm state, and that is this potential function, denoted V here. And in our case, it depends on these two components in a very simple way. Namely, we have the log distance to the optimum. So this is this thing I told you that will decay by a constant in every iteration if we have linear convergence. So that's kind of set because that's the behavior we want to describe. And then it depends in some way, which I don't know yet, some function of the other part of the state, which is about how well or how badly are my parameters adapted. And all I'm asking here is that this is a non-negative function. So for the drift experts, yeah, in general, like going back one slide, everything here is unbounded. There is no lower bound on the domain, which I'm using, and that's actually something I need. And even the single steps I can do are unbounded towards the left, and that makes all that analysis a bit tricky. Right, so intuitively, if I do a very good next point here, that's very close to the optimum, that logarithm can become arbitrarily negative. It's of course very unlikely, so all the expectations are well defined, but technicalities, that's somewhat nasty. And importantly, this, what I call this penalty term psi here, that's just any non-negative function of the state. And you can think of a potential function as basically, I mean, computing a scalar, a numerical value that says how bad is my state. Like the ideal thing is I solved the problem. I found the zero vector. Okay, we'll never really get there in continuous space, but this becomes the minus infinity. So we want to drive this on the real line kind of to the left towards lower values. And that's also, that means this penalty function somehow will take large values for bad configurations, for not well adapted shape, for like a step size that's completely off, and small values for good configurations. And the question is, how does that thing look like? Okay, but then how does the analysis go? Let's say we could show for some function here that this thing decays by delta in expectation, but then our drift theorem becomes applicable. Then what happens? So we start somewhere. We have some initial distance to the optimum and some initial shape, step size, and so on. If we decay by delta in each iteration, at some point, we can't decay this psi anymore because it's non-negative. It starts at 10, you reduce by 1 in each iterations. After 10 iterations, it's 0. You can't decay it anymore. So it has to decay the log norm m, and that's exactly what we want. Yeah, so now we make optimization progress, and that's also the order, the sequence in which that happens. We first adapt, say, the covariance matrix. Now remember this actual plot of CMA-ES. It takes a while until all the eigenspectrum is well adapted. And once that is the case, we make fast progress here. There's no more progress to be made here up to random fluctuations. And that gives us then some linear convergence rate that directly basically is described by how much progress do we make. Okay, now this was this technical note I basically already made for the drift experts. This is a kind of bit nasty case, but I'm pretty hopeful that we get a good grasp on that by means of writing down the right technical prerequisites, which are still somewhat to be figured out. Okay, so as I said, the big task now is we have to construct this penalty function. And this is the penalty function we used in the Gecko 2018 paper, like basically the first real drift analysis of an evolution strategy, 1+1 ES on sphere. So couldn't get any simpler. This is essentially like this log deviation of the step size from where it should be. So there is a well-adapted range, which is defined somewhat ad hoc. And then if we have a too small or too large step size, it just goes up, and then we have to figure out by what slope and what not. And that led to like nasty case distinctions. But in the end, we were able to show there is a positive drift. So, well, if we can compute it or bound on it, we have a convergence rate actually, which was nice. So that works for the 1+1 on sphere. This can be extended to other problems. Yeah, so actually extending to what Yuhei and Daiki didn't introduce so much overhead, but I have no idea how to extend it to more powerful algorithms. Problems, fine. Algorithms, problem. Yeah, nobody knows how to do that for CMA-ES. I show you, of course, some routes to go there, but right now, so here's where we stand. We do get, actually already Jens Jägersküper got the correct dependency on problem dimension on problem characteristics in some sense. Yeah, so how ill-conditioned is that ellipsoid, say? We get convergence rate if we have some delta, right? And we also can say how long it takes to adapt the parameters. That's basically just the initial penalty term value divided by delta. Yeah, that's the time it takes to drive this to close to 0. So it's very nice. That gives us kind of detailed analysis of what's going on. But, well, main problem at this point, we can't do covariance matrix adaptation. Of course, I want to do that. So what I have to do, what I do in my research is request for that penalty term so that we can do CMA-ES. Okay, so discussing that with some like very experienced theoreticians doing drift analysis for many years, I basically arrived at the decision to follow one route among the following options. Yeah, so how this usually goes is you invent some potential function, which in my case boils down to inventing some penalty term that just falls from the sky. There's no really good constructive way to get that. You have to use your intuition about the algorithms and the problems. So, and once you do that, well, I see two routes. One is what I call the deductive approach. That's how you usually approach that, right? I mean, you then take that term, it's there for a reason, you have used all your intuition, so then you try to prove that it actually works, so that it gives you drift. If that works, it's cool, you're done, it's fine. However, if that does not work, yeah, why? I mean, it's like getting a segmentation fault in programming as an error message. It's not that informative. It will get you somewhere, but maybe, you know, it's not what you wanted. Could be you were just not good enough at proving stuff. Could be that the statement doesn't even hold. You're trying to prove something that doesn't hold. That's an impossible task, of course, right? So how do you know? I mean, often during the process, you get some idea of why it fails, where it fails exactly. Maybe not. So I was like, oh, maybe I want to know a bit more. And that's why Well, I also considered this thing I called, or I consider as an inductive approach. So instead of failing and seeing maybe not finding out why, let's better empirically check if we actually get drift. Yeah, so let's maybe just simulate, approximate that drift by running the algorithm and checking, does this potential function actually go down? Does that happen starting from every possible state? If so, I have more confidence in that I'm actually trying to prove a statement that really holds. So there is hope to get a proof. And of course, if you then find in your simulation that there is a certain part of the state space where your potential function does not do the right thing, so it's not a proper description of the algorithm dynamics in the sense of potential function going down, well, you can act on it, right? You can iterate, maybe add another term, modify a term, see if you then get drift. And I asked basically which route should I take? And the answer I got from the theory guy was, it depends on how fast you think. I guess that's a fair point. Yeah, so if you can basically look at this term and after sitting down for an hour, actually say, I'm pretty confident that this will work, yeah, go for it. If that's not the case, maybe it's better to try empirically first. And now it turns out the terms we have here for CMA-ES are not easy, are not nice. So that's why I thought, okay, maybe I'm not the fastest thinker or whatever, but it seems more safe to me to take that inductive road. Okay, and that is what we did. So the idea was we want to find out, given some candidate potential function, does our algorithm actually reduce this potential function? And does it reduce it uniformly? So you need some lower bound delta that is positive and that holds everywhere. Yeah, so this is not trivial because our state space is not compact. Okay, how do we find out? We have a continuous space of states. We can't try them all. So let's do something approximate. Let's put a grid on our state space that's hopefully well chosen, that covers the interesting aspects. And for each grid point, but that's this green point here, we can just then do a Monte Carlo simulation. So we run the algorithm for one iteration and get a successor state. We can do that many times, and that gives you, say, this red cloud of points. Right, you can do that 1,000,000 times, and then the slide is full, okay, but you see there's some weird distribution depending on what your algorithm does. And then you can basically do like a Monte Carlo approximation of, yeah, this expected value by means of just simple averaging of the potential in the successor states. Yeah, you do that for every grid point, and if all these expectations are like have the right sign, well, it's finitely many, so you'll get your lower bound that's uniform. And you have to really look at this and decide, is that good enough or not? And it gives you some idea. And we, of course, we can visualize the result. And that's what we did. Actually, for CMA-ES in 2 dimensions, we have a 3-dimensional parameter space or state space. And this is now a 2D section through the space. And what you see here is basically our first attempt of a function. And green means the good sign, the sign we want. White is kind of exactly on the edge, and red means, oh, it goes backwards. Damn, this is not the potential function that works. So then you can go ahead and see, yeah, what states are that? So this is actually now some normalized step size, and this is conditioning of these ellipsoids, or the conditioning mismatch of the 2 ellipsoids involved. Yeah, let's try to do a fix and add 1 more term. Yeah, okay, improved, works better, and then you can actually iterate and maybe eventually arrive at something like that. Oh, everything is nice. However, the price is what we get is a huge nasty formula of many terms, and there were smoothing terms in there which we don't really want, and there's basically not much hope to take that huge formula and do complicated bounds with it and really understand like the algorithm in these terms. So yes, it works in principle, but we don't get the, or maybe, right, I'm not the right guy to find that nice analytical formula that does it. So, well, didn't lead to a proof yet. Okay. But at least I don't spend time on trying to prove something that doesn't actually work or doesn't even hold. So, turns out that once you have accepted this general methodology, like let's use a grid and parameter space, let's make it wide enough to cover the interesting dynamics and whatnot, you can start playing with that and actually do something powerful. So I thought at some point, okay, why do we take this analytical formula, which we tune and tweak, and then evaluate it on a grid to see if it works? Can't we turn that around and just say, oh, let's start with a grid and say, what if I could assign any value to any grid point? Take complete freedom. And can I maybe do this in an optimal way? Yeah, so if I take that freedom and I only care for the grid, can I design an optimal potential function? Turns out this exists already, for example, under the name canonical drift. And the idea is simply, it's kind of a killer argument for like, why is additive drift enough for everything? An existence thing. So if we would say our potential function is simply what we call this expected hitting time, that's now this language of drift theorems, that's simply the runtime it takes you to stop. So say we stop our algorithm if we are in a vicinity of 10 to minus 10 of the optimum. Yeah, that was this goal position in the drift theorem. We just say, okay, how long does it take to get there? From every state, that's a well-defined function, as long as we get there at all, right, with probability 1, which is not the problem here. Okay, so if I take that as a potential function, I will obviously reduce that function and expectation by 1 in every step, simply because I'm doing runtime, right? If I spend 1 step of my runtime, the expected remaining runtime goes down by 1. So delta is 1. And actually, this has one more advantage. The bounds I will get are not really bounds. I mean, I have an exact description of what happens, so I can get kind of arbitrarily good lower and upper bounds. It will be bounds in the end still, because we are only doing a grid and we have to take care of what happens if we are not on the grid. Yeah, but somehow intuitively, this can get us arbitrarily close to an optimal analysis. Problem, like, why isn't it then done this way all the time? Obviously, because this is not an explicit function of my state variables, right? That runtime is a function that exists, but I don't know how it looks like. I don't have a closed form for it. So what I want is a function where I can just plug in my initial state and say my target precision, and then that function tells me, oh, look, your runtime will be X, and of that, so much goes into the penalty term, so that's how long that adaptation phase takes, and that's how long that convergence phase takes. But if I don't have that function in an analytic form, right, I can't do that. So what's my analysis worth? And now it turns out, restricting myself only to the grid, I can actually do that. And so for those who went to Alexander's poster yesterday, you have basically seen like a particular application of this. Here I want to do that really from a bird's eye perspective and try to give you a really big picture about that. So in order to motivate that, I entered foreign territory, which is the discrete world. And I did this for a 1+1 EA with standard bit notation on 1max. So let's start with this figure. This is an illustration of the algorithm dynamics. So we have 100 bits in our bit string, and this is the state before and after an iteration. And these are probabilities. I've subtracted 1 from the diagonal because otherwise the diagonal is so dominant that you don't see much. So essentially, most of the time, we stay where we are, which is the diagonal, but then we move to the right from time to time by typically very few bits. 1, 2, 3 probabilities go down quickly. And from that information, you can easily compute the expected progress in each state, which you can really reduce to the number of 1 bits, of course. Yeah, so of course we have 2 to the n different bit strings, but we can reduce it to 101 different states, 0 to 101 bits, and basically get this expected progress. So if you have 0, 1 bits, then you improve by 1 bit on average, just by the way standard bit flip mutation is designed. Of course, if you have an optimal string, you're not improving anymore. And this is just what comes out. And now you can take this thing and basically solve a linear program for the goal that we have a potential function so that the drift over all states is always 1. And that is the potential function we get. So this is not the standard function that is used for analyzing 1 plus 1 ES on 1 max. That's simply the 1 max function itself. Now I say, okay, I want to do the analysis with this different function. And then I get a constant progress of 1, expected progress of 1 per step. In other words, this potential function is expected runtime. So I can solve it exactly. So this is the optimal lower and upper bound. If you want to know how long it takes, plug your initial state in here, and that's the expected runtime. That's not only, doesn't only work for this simple one, I can also do it for leading ones. Now, okay, these numbers are significantly lower, like 1 max, or sorry, leading ones takes longer than 1 max. We know looks a bit different, the shape. This shape looks a bit different. These transition probabilities, of course, also look a bit different. The thing that stays the same by design is the progress in each state is exactly 1. So again, the potential function, expected runtime, can be computed in these cases. Let's get a bit more fancy, even binary value. So binary value, now we can't aggregate. We really have to deal with this exponential number of states, so it's very limited what I can do here computationally. So this is for only 10 bits, 2 to the 10, 1024 different states. Yeah, and well, now this figure, like we don't really have the resolution. I don't know if you can see like these thin lines over here. That's basically the jump that comes from flipping the highest bit. There were some other lines in here. Now it doesn't show well on the beamer, okay. And actually the progress decays nearly perfectly linear with that value of the number, that binary value number. But the potential function that you get looks kind of fancy, right? But that is, again, creating constant drift of 1. So constant expected progress in terms of that potential. So again, this is the expected remaining runtime if you are in some state. And this, all of that can be computed more or less like in closed form, okay. How about our evolution strategies? Like there's not going to be any closed form. Sorry, all these integrals are just horrible. They are nasty, but we can approximate stuff rather easily. So again, I said like basically we start from our grid, and the question was, what if I can assign any value to any grid point? Again, right, I run my Monte Carlo approximation of like what is the successor state of the algorithm dynamics. So I can essentially get something that is rather close to this transition matrix. There's some rounding involved and so on, but it's a good enough description of algorithm dynamics. And then I can do exactly the same thing. The only difference is I stick to my ansatz for that potential function. I still have that log norm m term in. So basically this determines my penalty term, like what is the progress, and then I have to basically subtract that actual optimization progress to get the penalty term. And if I do that, I get similar figures. So this is essentially the algorithm dynamics on the theta part. Now for a very simple 1 plus 1 ES without covariance matrix adaptation on the sphere function. So essentially state before, state after the step. And there are always 2 options. Either you sample a successful or an unsuccessful offspring. If it's unsuccessful, you jump a bit left from the diagonal. Like you basically move a little bit to the left. If it's successful, you move to the right 4 times as much, at least. why at least and why this effect fans out here a bit. I'm not going to go into details. Generally speaking, these are much too small step sizes. Here it's a 50-50 thing. These are much too big step sizes, so basically all steps are unsuccessful, and this is the region we want to be in. And this is the progress we get, this expected progress we can derive directly basically from this matrix, or by other means of running the algorithm, of course. And then this is what comes out of the linear program. So we have some nice penalty function. And if I basically take both of them together, I again get a constant drift of the whole state space. This is now not one, but that doesn't matter, right? It's just linear. I can just linearly rescale my potential function. So essentially, these two things together, again, give me expected runtime as a potential, somewhat approximate, because there's this grid involved, of course. Yeah, but essentially it works. And now compare this function to what we used in the initial analysis. It's not too far, yeah, but this is a much more detailed description of what's going on. Of course, at the price of having far more parameters, obviously. So there are many, many technicalities involved. Like just for the Markov chains, I glossed over many details. It's a bit more complicated than you would think naively. So one thing that's nice is the choice of the grid turns out to be rather uncritical. We replaced the Monte Carlo approximate integration with something better to really get a priori bounds. We are currently ignoring floating point errors because they are small anyway compared to the numerical, like the integration errors. And what we can do is we can actually propagate our errors from all these expected values to the penalty term. So I can tell that my penalty term is really in some sense close to optimal on the grid. And what we want to do with this is we want to turn it into a proper computer-assisted proof technique. That's not really ready yet, but we are close. And what we need to do is basically we need to fill in the gaps between the grid points. We'll use some Lipschitz constant of the drift function itself for that. And we have to also say what happens outside of the grid, right? Because this grid is finite. It's not the whole integer lattice. We are having computers, finite memory, finite compute. So somehow we need to control asymptotic effects with analytical arguments, which is doable. Because if our grid ends, say, at a much too small step size, we basically know what happens. If I make it even smaller, no surprises are to be expected. Yeah, and one big caveat here is that this is only possible for small dimensions. For one thing is the numerical integration is costly, and the other thing, my grid dimension will explode. So this will be exponential. This is not, in this world with our compute, not very scalable. So what did we achieve? I'm pretty sure, and I have a kind of pilot study as an excellent bachelor thesis, basically just finished to do this also for covariance matrix adaptation. No results yet, but hopefully soon. With this, I hope I convinced you we can control the convergence rate. That's basically having a value for delta. And we can even control the duration of the adaptation phase until we get there. That's the initial penalty term divided by delta. It's really that simple. But we can only compute that for single problem instances. So we'll not get parameter dependencies, as for example, LIACS did, on dimension, on problem instance properties. Okay. And it's only computationally feasible in low dimensions. I'm not so concerned because I think that most interesting effects of covariance matrix adaptation do show up in 2 dimensions. But of course, it's a limitation that's worth noting. And with that, I want to conclude. Time's up anyway, basically. So I hope I convinced you that analysis of CMA-ES is progressing significantly in recent years. In particular, Amon's Markov chain results are noteworthy. So convergence is solved. Linear convergence at a rate that's independent of the problem instance, but we don't have the rate. And for many reasons I showed you in this presentation, I think that drift would be a very valuable addition to that analysis. But we are close, but we are not exactly yet there yet. And with that, I would like to thank in particular two members of my group, Stefan, who did all the struggling with what I called this inductive approach and like doing large scale computer experiments to get an idea of what is a good analytical function, and Alexander, who is here. This is actually him at his master's ceremony where he got a prize for his thesis, which actually deals with this problem of how to fill in the gaps between the grid points. At least that's one of the results. And I also want to thank you for your attention, and maybe you have some questions.